Hey guys, today's video is going to focus on the equilibrium constant, what it actually means quantitatively. And this video is also going to serve as an answer key to the Le Chatelier's principle problem set. And in that problem set, you're being asked to evaluate whether a equilibrium system, when stressed, will shift left or right towards either reactants or products in order to mitigate that stress and return to equilibrium. Before we get to the answer key, just a couple quick things in terms of what that K value, numerically, what it really tells us. So, just a reminder, when we talk about chemical equilibrium, this is going to be a state where the concentrations of all reactants and products remain the same, right? They remain constant. And what that implies is that the rate of the forward reaction is equal to the rate of the reverse reaction. And we actually call this a state of dynamic equilibrium. It isn't to say that no reaction is occurring, like something is taking place. The forward direction and the reverse direction are both running simultaneously, equal rates, reactants being converted to products, reforming reactant. It's not like this situation where nothing is taking place. It's just maybe macroscopically to the casual observer, we might not see anything. When we talk about this K value, what it's really telling us, this equilibrium constant, it tells us essentially whether products or reactants are favored. And we find that when K has a value larger than 1, our products will be favored. And when K has a value less than 1, our reactants will be favored. And this is because when we go to set up our K expression, just remember that we always have product over reactant, right? Now, obviously, it's a little bit more complicated than this. We might have multiple products. We might have multiple reactants. We need to take into account coefficients from a balanced equation and how that manifests in terms of exponents. And we'll take a look at that here in a moment. When we talk about this K value, there is only one K value for a particular system, so whether it's a reaction or process, at a particular temperature. So these K values are actually temperature dependent. That being said, there's an infinite number of equilibrium positions, and we're going to see this again via math here in a moment. So when we talk about a particular, again, reaction process, initially we have some concentrations, right? We go into this thing with maybe some reactants. Now, your equilibrium concentrations will be dependent on the initial concentrations, but the equilibrium constant, as this term constant would imply, is not. Now, this language in these last 2 points here might be a little kind of weird. You'll see exactly here what I mean via the Haber process. The Haber process is a method by which we can take nitrogen and hydrogen and we can actually convert it to ammonia, okay? And what we're going to do is we're going to study this reaction at 600 degrees Celsius. And so imagine we go into this thing with some initial amounts, right? And let's just say we're talking about molarity, for instance, okay? So moles per volume. And we have 1 mole of nitrogen and we have 1 mole of hydrogen. Well, as you might expect, as the reaction proceeds, obviously we're going to generate some product, okay? So maybe hours go by, days go by, weeks go by, whatever the case is. And what we find is that our equilibrium concentrations, okay? So when the reaction has appeared to stop, though it hasn't, again, the forward and the reverse direction of the reaction are both still taking place. What we would find is that, yes, we have converted some of our reactant to product. Again, these are our initial concentrations here. These are equilibrium concentrations, but we still have a fair amount of our reactants left. It's not like we've entirely converted reactant over to product here, right? So this reaction doesn't really go to completion. Now, if we wanted to set up the equilibrium expression, what we do is, again, our K value, that equilibrium constant, is equal to products over reactants. We have to remember to convert, or not convert, but take into account our coefficients and how they manifest as far as exponents in our equilibrium expression. We plug in our equilibrium concentrations, and we find that we get a K value of 6.02 times 10 to the negative second. And again, what this value literally tells us is essentially the ratio of product to reactant. And earlier we said that whenever you have a whenever you have a K value that's significantly less than 1, our reactants are going to be favored, right? And that's what we found, right? We have a lot of reactant that never really reacted, right? It kind of stayed put, okay? So imagine that, and that's what the statement says here, right? Because the value is much less than 1, this means the reactants are favored, not much product forms. What if we do something a little bit different, okay? What if we take a look at a situation where we're given the following initial amounts, these initial concentrations? Well, we just got done saying that this reaction doesn't really work all that well in the forward direction. And if a reaction is not thermodynamically favored in the forward direction, that is to say that perhaps maybe it's favored in the reverse direction. So imagine we have ammonia, right? We have like 1 molar worth of ammonia, and we're actually investigating its decomposition, right? Its ability to kind of decompose and to generate nitrogen and hydrogen. Well, over time, if we were to restudy the system, we give this reaction kind of a chance to proceed, we find that a lot of the ammonia goes away, right? Our equilibrium concentration, we're only left with 0.203, and we form actually a whole bunch of our quote-unquote reactant. When we plug these new values, these equilibrium concentrations in, we find we get the exact same K value, right? And we could have anticipated this. We could have anticipated, because our reactants are highly favored because we have a K value less than 1, that this decomposition would actually proceed in the reverse direction quite well, okay? Now again, that was kind of a quantitative approach to what the K value actually means. Let's get a little bit more conceptual. And let's jump into these Le Chatelier principle / shifting type problems, okay? We're given the following system, H2S plus oxygen yielding water and sulfur dioxide there. We're told that this is an exothermic reaction. That's what the sign of delta H means there. The negative means that we are releasing heat as a product. So we can write that in straight away. If I want to write out the equilibrium expression, again, our K value is equal to products, so our water, taking into account the coefficient and how, again, that becomes an exponent, multiplied, so it's the product, and multiplied by SO2, again, raised to the second power there. This is going to be all over in our denominator. We have H2S squared times by oxygen cubed. So this is our equilibrium expression, okay? What we're being kind of tasked with now is trying to figure out, given the following stresses, right? That's what we're going to be evaluating, is different stresses. We're trying to figure out, does the equilibrium shift right, shift left, or perhaps is there no change, okay? So in all cases, we are assuming that this reaction is at equilibrium. Now in this first case, what we do is we come around and we add extra oxygen, okay? So that's what we're doing, we're adding extra oxygen. So if we look at our K value, we just increased this amount, okay? And when that happens, what this means is that now our K value is too low, right? If we increased our denominator, that means our K value is too low. And in fact, when we're not at equilibrium, we don't call that K anymore, we actually call that Q. So Q, that's called our reaction quotient, is a way to quantify whether we are at equilibrium or not, right? If it's too low or if it's too high, if we're not quite at equilibrium because we've placed some stress on the system, we just say Q instead of K, okay? Well, obviously, I think conceptually this should make sense. If we've decreased the value of Q, or you might say the value of K, but really Q, we need to find a way to increase that, right? So what we need to do is we need to increase our numerator. Well, the only way to increase our numerator is to increase the amount of product, right? So if I want to find a way to essentially get rid of the oxygen that we just added into the system, well, I'm going to go ahead and decrease that. The way that I can decrease it is by reacting it with our H2S. And in doing so, I form more water and sulfur dioxide. Okay, so again, just to recap, we're at a system of equilibrium. That means that everything's kind of like perfect. right? And we disturb this system. And in disturbing it, we went in and we added extra oxygen. We increased this amount. Well, if we've done that, the way that the system is going to respond, it wants to reduce that amount. And in trying to reduce it, we will shift to the right, right? The only way to reduce this amount is to react it. It is to shift to the right to form more product. And so this arrow in red here is what we initially did. And then to kind of, do the opposite, we're going to react it, which means this is going to go back down. In turn, we're going to decrease the concentration of our other reactant. We'll increase the concentration of our two products. And now Q gets restored back to K, right? So again, Q is a way to quantify conditions that are not at equilibrium. K is reserved for conditions that are at equilibrium, okay? All right, let's move on to B. We're expanding the container at a constant temperature, okay? So let's just take a look at what happens. When we increase the volume, what this does is this decreases the pressure. That's the stress that we've placed on the system, is that we've decreased the pressure. Well, not we, but the system is going to find a way to increase the pressure. That's the goal, right? That's what this equilibrium system now wants to do in order to get back to equilibrium. The only way to increase the pressure is to realize that you have 4 moles of gas on the product side, and you have 5 moles of gas on the reactant side. Well, if I'm trying to increase the product, if I'm trying to increase the pressure, I'm going to shift in the direction where there's more moles of gas. So I know that I'm going to end up shifting to the left for part B. Again, if we, as like a chemist, have increased the volume, thereby decreasing the pressure, the system will respond in a way to increase the pressure. It shifts to the left to increase the number of moles of gas, thereby increasing collisions and therefore the overall pressure. A way to kind of quantitatively think about this is to imagine that these concentrations, again, are in mole per liter, right? So mole per volume. Let's say that we just, double the volume of this container. Well, what happens to our K value is whatever our concentration was, we've just halved it, right? If we double the volume, so now it's like mole over like 2V, whatever the concentration was, we have basically just multiplied it by 1/2, okay? So if I plug in a 1/2 and I square this, again, the 1/2 is what would happen to these concentrations if I doubled the volume. It's just kind of a something to work with. Again, 1/2. In this case, we have 1/2, but this is cubed. These two could cancel out. We're left with 1/4 over 1/8, which means we have 8/4, which means we have 2. Okay, so what we've done is we have taken our K value, which again is no longer K. We've made it Q, essentially, okay? And because we now have way too much product, right? We've increased this value. Because we've increased the amount of product, we want to find a way to get rid of that product. Our numerator, our overall value is just too high. The only way to get rid of product is to react it, and we push to the left, okay? So in these first 2 examples, we got a little bit kind of quantitative. We took a look at things in a fair amount of depth. These next ones we're going to work through quicker, and I think we can find a better way to probably just conceptualize things and make things a little bit easier for you all, okay? All right, so going back to this equation, we're going to remove SO2. Well, if we remove SO2, if this is what we've done as a chemist, if we've decreased the amount, the system wants to find a way to increase it, right? We've done this. The system is like, nope, not having it, and it will shift to the right in order to form more of it, okay? In part D, if we raise the temperature, the system will respond in a way to do the exact opposite. It will find a way to essentially decrease the temperature. So again, going back to what we said earlier, we know that this is an exothermic reaction because of the negative sign for delta H here, for our change in enthalpy. Therefore, we consider heat as a product. Well, if we raise the temperature and the system wants to find a way to lower the temperature, we want to get rid of heat, right? We want to essentially use it up or consume it. And in doing so, this reaction will shift to the left, and our products, also heat, are going to react in order to form our reactants, as it were. So we will end up shifting left here, okay? And then in part E, this last one here for the first question, imagine that we are absorbing water vapor, okay? If we're absorbing water vapor, that is to say that we are going to decrease this amount. Well, again, if we are decreasing this amount, the system wants to find a way to increase it, so our reactant will continue to react to reestablish equilibrium and kind of replenish the water that we have removed or absorbed. And so we have a nice shift right here, okay? Let's push on then to question number 2. The very first task is to write out the equilibrium constant expression below, okay? Our K is going to equal the concentration of nitrogen monoxide multiplied by the concentration of nitrogen dioxide over N2 over O3. No exponents necessary because it is a 1-to-1-to-1 relationship between our reactant and two products there. So in this first one, we're going to add additional N2O3. Well, if we increase this amount, the system wants to find a way to decrease that amount. In order to decrease the amount, the only way that can happen is if it decomposes, right? We shift to the right in order to form more product. For part B here, we decrease the container size at a constant temperature. If we decrease the container size, so decrease volume, the ramification of this is that we've just increased pressure. The system now wants to find a way to decrease the pressure. Okay, this is what we've done here as the chemist. This is what the equilibrium system is going to do in order to reestablish kind of the correct relationship between reactant and product. We have 1 mole of gaseous reactant. We have 2 total moles of gaseous product. In order to decrease the pressure, we will shift to the side with fewer moles of gas. That is going to be your reactant side. So we have a shift left for part B here. Moving on to part C. Hopefully we're kind of getting the drill at this point. If we add nitrogen monoxide, the only way to decrease nitrogen monoxide is to shift to the left. Nitrogen monoxide will react with some nitrogen dioxide, and we will increase the concentration or perhaps the partial pressure of our N2O3 there. So again, this is a shift left for part C. As far as part D goes, if we lower the temperature, we know that we have to be doing something with our delta H term. If it's positive, this means we have an endothermic reaction on our hands, where we're going to consider heat to be a reactant. If we lower the temperature, the system wants to find a way to essentially increase the temperature. And so in doing so, it shifts to the side where heat is. It wants to actually produce more heat. And so we have a shift left in part D here. Moving on to part E, if we remove some of the NO2, the only way to increase now the amount of NO2, which again is how the system is going to respond, is to shift right in order to form more product. And this last question here might have thrown you for a loop. This is a great question. It says adding helium gas, okay? How is this going to impact our equilibrium position? Like, are we going to shift left, shift right? What's going on here? Let's rewrite these concentration as far as like mole of nitrogen monoxide over, and this is again is like the liters of the container. I'm just going to write CONT period there. Okay, that's what that really is, right? Moles of nitrogen monoxide per the liters of the volume of the container. This will be multiplied by moles of the NO2. Again, over the liters of the container. And then we have our mole N2O3 over, again, the liters of the container. So I've just rewritten this. And the question is, well, how does helium impact any of this? it is not affecting the actual size of the container at all, right? It's also not impacting the amount of moles you have of any of these things. And so the answer is that there's going to be no change. And just kind of a summary statement there, we're going to say inert gases, so gases that like don't react with the system at all, like they don't actually engage with the reactants of the products. Inert gases have no bearing on the equilibrium position, right? The idea that by adding some helium to this case, or to this container rather, we are not going to have a tendency to shift left or right. All right, thanks guys.